Okay, well, let's get started. So today, we'll just go over a lot of, let me just say, numeric examples. I don't think, once you get the hang of the numeric things, you could probably start doing the theoretical questions. But today we'll just see how, like, it works for like specific fields. Yeah. Because I mean, if I just told you, let F, K be field extensions, it might be hard to think of what's happening. So, yeah. Okay. Definition. So we know what an algebraic element is, right? And a simple extension. So we could think of like, you know, a ton of simple extensions, right? You just do one simple extension after another. So you just keep attaching algebraic elements. So an extension field E of a field F is algebraic extension. Hopefully you all know what this stands for. Extension of F if every element in E is algebraic over F. Yeah. So there's no transcendentals here. And if extension field E of a field F of finite dimension n, finite dimension n, vector space over F, then if E, let me just say if E of a field F is a finite dimensional vector space over F, then E is a finite extension. Is yeah, then sorry, grammar's bad. E is finite dimension, finite extension of degree n over F. Yeah. So we call this degree, you could think of this as like the degree of the irreducible polynomial if you're just adjoining one element. We call this E to F. Yeah. Be degree n of E over F. So for example, like this, we say this thing is 2. Yeah, because this is a 2-dimensional vector space over Q, right? It's generated by the basis over Q is 1 and root 2, right? So we say this is like 2, for example. So let me just say a note finite extension does not mean finite field. Yeah. I mean, this is a finite extension of Q, but clearly this is not finite, right? I mean, Q is not finite. So don't mix those two terms up. Yeah. And similarly, you could think of it as if E is a finite extension of F, and what if it's a one-dimensional vector space over your field? If you think about it, that just means you're the field itself, right? Yeah. So if you're a finite extension, which means you're either itself or it's or bigger, but if you're only dimension one over that space, you must be equal. Yeah. And there's a theorem that says a finite extension, if your extension is finite, it must be algebraic. So field E of a field F is algebraic extension. Yeah, so basically this is saying if I tell you there's the finite field extension, you can't be adjoining transcendentals, yeah, over your base field F. Because if you adjoin transcendental, it's like infinite, yeah. So let me ask you: is the opposite true? If I have an algebraic extension, if I just keep adjoining algebraic elements, is that extension field finite over your base field? Yeah, I mean, there's a lot of examples. I would just say take Q adjoin all n roots of 2. These are all algebraic, so this is an algebraic extension because all of these satisfy like this, right? Yeah, but I guess I'll just say, how about this? Yeah, let's just say real n of 2. So, but here, right? These are algebraic, but it's not finite, right? Because if this was a set number, roots of 2 to Q, right? Let's say this was, pick your favorite number, like M. Then this can't happen because then M plus 1 root of 2 would not be in here, right? Because this is a root of x to the m plus 1 minus 2 is 0, and this is irreducible by Eisenstein. Yeah. So you see it can't be finite, but it's still algebraic. Let me just say, so note, but this does say that note transcendental elements are like, infinite degree. So, which is normally for the purpose of this class, we normally study like algebraic elements. Okay. Everyone clear so far? Yeah, how do I say this? So one way to think about it, at least why this is true, is if you recall, right? If I had like one, it's generated by 1 and root 2, right? The reason for this, why we don't have anything bigger, like why we don't have this, is because we can express this in terms of that, right? Because like x squared minus 2 is 0. So like root 2 squared is 2. Yeah. So once I hit root 2 squared, I sort of go back to constants, right? Like 1 plus 1. Yeah. But transcendentals, there's no relation, right? There's no polynomial. So you see, the reason why it's infinite is because if you have a transcendental element u, there's like, infinitely many. It's like an infinite dimensional vector space, right? Because you need to take like the fraction field, right? So that, so it sort of makes sense why it's like infinite degree. Okay, moving on. Tower law. I call this tower law. The book doesn't, but it sort of makes sense why it's tower law. So if E is finite extension field of a field F, and K is finite extension field of E, right? Then K is finite extension over the base, over F. And what else do we know, right? Like this thing is true, right? So we have this certain picture, right? E is a finite extension of F, K is a finite extension of E. Then this is also a finite extension. So finite with finite gives finite. And we know more. What's the degree? It's the product. So it's K to E, E to F. Yeah, so just think of it as, these two cancel and then you get K to F. So for example, if this was extension of degree M and this is N, then the extension of the whole thing is Mn. Yeah. And we actually know the basis. So if this is given by like beta 1 to beta n, and the basis of E over, so this is basis, so basis of K over E, yeah, not over F, right? Because this is, we're viewing the n here is the dimension of the vector space K over the field E, yeah? So, and then let's say this is my basis, basis E over F. Then I'm pretty sure your professor proved this, but the basis elements for K over F, basis for K over F is given by like alpha I, the all products of them, yeah? Alpha I, beta J. So, I mean, you could use induction and prove that in general, Fi is field for I equals 1 to R, Fi plus 1 finite extension of Fi, then Fr is finite extension of F1, right? And it's just tower law over and over. So Fr to Fi equals Fr to Fr minus 1, Fr minus 1, Fr minus 2, right? All the way to F2, F1, right? And then they keeps canceling, right? Is everyone clear on this? Yes, no? Okay, so we're going to be using tower law a lot, yeah? So let's do the first question, right? So find degree of Q adjoin root 3, root 2 over Q, yeah? So I know that this contains this, right? I'm just going to choose one, but this certainly contains this, right? And this certainly contains this. Does everyone agree? So this is extension 2, yeah? I mean, x squared minus 2 is irreducible over Q. So, and I know here I'm sort of adjoining root 3, right? So I know I root 3 is a, sorry, not plus 3, minus 3. Root 3 is a root of this. Agree? Now, it's possible, we know this is irreducible over Q, right? But it's possible that, it's it's reducible over the bigger field. It's reducible over Q adjoining root 2, right? It's possible. But we know, so we know that this thing, but we know since root 3 is a root of this thing, well, where's my parenthesis? Uh, I don't know. I wrote bracket instead of parenthesis. To Q adjoining root 2, it's at most 2, right? So it's going to be either 2 or 1. Does everyone agree? Because, I mean, the polynomial root 3 is degree 2. So it's either reducible, in which you're degree 1, or it's irreducible over Q over 2. Okay, now let's assume it's 1. Yeah? What does that mean? Can anyone tell me what that means? So if I go back to, where did I write it? Yeah, so if we go back to here, right? If E is a finite extension of F and the degree is 1, then E equals F, right? So certainly this is finite extension because, I mean, it's certainly finite. It's smaller than or equal to 2. and so if I assume it's 1, well, they must be equal. So assume 1, then these two fields are equal. Yeah? Does everyone agree with the argument? So if these two fields are equal, root 3 must be in here, right? Root 3 must be in here. Does everyone agree? Since these two sets are equal and one of the sets has root 3, then the other set must have root 3, right? So we could check that this isn't possible, right? If root 3 was in Q adjoining root 2, well, how does an element in Q adjoining root 2 look like? It looks like A plus B root 2, right? Where A, B is in Q. Everyone agree or follow so far? Okay, well then let's let's square it, right? So 3 is A plus B root 2, A plus B root 2. What is this? So that's A squared. I'm bad with math. What is this? 2AB root 2? 2AB root 2 plus 2B squared, right? So I get 3 plus 0 root 2 is A squared plus 2B squared plus 2AB. So let's match the coefficients now, right? This with 0. And then let's match the constant terms, right? So I know from the blue underline, 2AB equals 0. Agree? So either A is 0 or B is 0. Because Q is a integral domain, right? So let's check the case where 1A equals 0. Then from the green underline, 2B squared is 3. And B squared is 3/2. And this is an issue because this would mean B is plus minus this. And this is not in Q. Yeah. And same argument for the other one. If B is 0, then A squared is 3. Then A is plus minus root 3. And this is not in Q. So you see root 3 cannot be in this field. So this must be a degree 2 extension, in which case Tower law tells me what? This thing is by Tower law. Join root 2. Oh, I hate this. Multiply Q adjoint root 2 to Q. So this is given by 2 times 2, which is 4. Yeah? Does everyone see this? And we know, so this is 2, and I found the polynomial of degree 2 that has root 3 as a root. It must be that that root 3 and 1 and root 3 generates this space. So the basis of this space right here, so let me erase this, right? The basis is given by 1 and root 3. The basis here is given by 1 and root 2. Yeah? And note when I write 1 and root 3, it's not over Q, right? Like I'm saying that this is equals the set of A plus B root 3 such that AB is in here, right? Because we are viewing this as our base now, right? So, okay, does everyone understand this? Yes? No? Okay, and what does the theorem say? So the theorem says if the basis here is beta 1 to beta n, alpha 1 to alpha m, then the basis is given by alpha I beta j, right? So we just take all possible products. So here, the basis, the four basis elements are given by 1 times 1, 1 times root 3, 1 times root 2, and root 3 times root 2. So the basis of, I mean, you should get 4, right? Because it's degree 4. So 1, root 3, root 2, root 6. Does everyone follow? Yes, no. Okay. So let's continue. So yes, so today is going to be pure. I'm going to give you explicit numbers. Yeah. So we're not going to do theoretical stuff like just let f be any algebraic extension, prove something, right? So we're going to do tons of numeric examples. So we all see how these theorems are used, and then hopefully by then you have a clear picture on like how arguments like these go. So let's continue. So let me make another question. Is Q adjoint cube root of 2 a field extension of Q adjoint root 2? What do you all think? No. Well, let's see. So if it was, right, then I certainly have something like this. Agree? But I also know Q adjoint root 2 is an extension of Q, right? Agree? Now here comes the issue, right? I know that what's degree of this? What's degree of what's the whole degree here? To Q. What is this? What's the irreducible polynomial of cube root of 2 over Q? You know this. Yeah, so this is degree 3, right? I mean, the polynomial is given like this. Okay, now what is this? Do you see the issue now? 2 does not divide 3. Yeah. So it's not possible for this to be a field extension, right? Because by Tower law, this has to be true, right? Q adjoin cube root of 2, Q adjoin square root of 2, Q adjoin square root of 2 to Q. So this times this, so 3 is equal to this thing. Times 2. And I mean, does it make sense to have a 3/2 dimensional vector space? Dimension is always an integer, right? So we see that this can't happen. Yeah. Okay. Does everyone follow so far? Okay. Okay, that's good. Okay, let's do something there. Let's continue. So example, find the degree and a basis for the given field extension. Yeah. So let's do this over, I'm not gonna write over here. Let's just say this. So I claim we have done this question already. So what is square root of 18? Like what happens after you simplify that? 3 root 2, right? So let me ask you, if q adjoin root 2, like q adjoin root 2 root 3, right? If I have root 2, do I have 3 root 2? Yes or no? If I already have the element root 2, yeah, I'm closed under, if you like, addition, right? Root 2 plus root 2 plus root 2, because I mean it's a field, right? So you see that these are just equal. This is like a trick question. Yeah, these are just literally equal. So and we solved this problem before. It's degree 4. I mean, I just did it like 10 minutes ago, right? It's degree 4, right? And the basis was given by this, right? And so you see, we're done. So okay, let's do something harder. uh Q adjoin cube root of 2 root 3. Yeah. So your intuition would be, maybe it's like 6. There are many ways to argue this, right? Since we have so many tools. So I'll give you one argument, using Tower law, since Tower law is like fairly new, I guess. Yeah. So we have the corresponding thing, right? So we have Q adjoin cube root of 2, and then this as a subfield, right? Everyone agree? And like, what is the degree here? 3. And what about here? 2, good. So by Tower law, so let's work out Tower law, yeah? Is everyone okay if I just called this like K? Sorry, so I don't have to write this all the time. Yeah, okay. So there are two Tower laws going on, right? I know K to Q root 3 to Q to root 3 to Q, right? That is K to Q, yeah? But K to Q can also be the other way, right? It's also K to Q cube root of 2 and Q of cube root of 2 to Q. And you told me that this is 2 and this is 3. So does everyone agree from here that 2, if 2 divides, so 2 divides this thing, 3 divides this thing, right? This looks ugly. Let me. So this thing has to be at least 6, yeah? Does everyone agree? Okay, and we're almost done. So let's just pick this one, yeah? Let's pick this one. So for here, right? I know that this is the cube root of 2 is a root of x cubed minus 2. Agree? So, I mean, I know this is irreducible over q. It's possible it's reducible over q adjoint root 3, right? I mean, we're not going to rule that out. We only know by Eisenstein x cubed minus 2 is irreducible over q, right? But it's possible maybe over this bigger field it's irreducible. But in that case, I know that this thing is smaller than or equal to 3. Agree? If this thing was irreducible over q adjoint root 3, then it's 3. If it was reducible, then it's smaller, right? Does everyone agree with that? Yes, right. Okay. But if this one equal to 3, then this thing is at most 6. So this is a nice trick if the two things here are like two different primes, really. So this trick only works if like you have like two different primes, but it's a nice thing. It's a nice way to see how tower rule works. So from here, you know that it's dimension 6, in which case this thing is irreducible, yeah, over q adjoint root 3. So the basis of, so again, we use the theorem, basis of k over q adjoint root 3 is given by 1 cube root of 2 cube root of 2 squared. And then basis of q adjoint root 3 over q is 1 and root 3. And then we just take all multiples, right? 1 times 1 is this. 1 times root 3 is root 3. Cube root of 2 times 1. Cube root of 2 root 3. Cube root of 2 squared and cube root of 2 squared root 3. So these are our basis, our 6 basis elements. Yeah. But arguing, we basically argued it was already degree 6 by using tower rule. Whoa, did I mess up? Oh, sorry, square root of 3. Thank you. As you can see, I'm bad with algebra, like pre-algebra, I guess. Okay, so yeah, so if I make like an algebra error, just tell me, because chances are I probably will. Uh, okay, but is everyone clear on how tower rule works? Yeah, yes or no? Okay, well, let's just do one more. Yeah, so let's do something harder. Yeah, Q adjoin root 2 root 3. So I'm not going to ask for the degree over Q. I'm going to ask for the degree over this plus root 3. So does everyone agree that, when I write over, it's assumed that this is sort of like, this is a field extension of this, right? I mean, clearly, if you have, clearly like this one's smaller, right? I mean, when you look at it, because if you have root 2 and root 3, then when you add them, you obviously have root 2 plus root 3, right? But I mean, it's not clear that my claim is that these are equal, but it's not clear a priori that if you just have this element, you have both of these, right? So we certainly see like the left one is like bigger. So let's write it out. So it's pretty clear that this one's bigger. And okay, so there are many ways to do this, right? Like we showed before that this was 4. Does everyone agree? I mean, I did this 20, is it 20 minutes ago? So if this field has what element? Like this field has root 2 and also root 3, right? And a field is closed under addition. So if you have root 2 and root 3, it's pretty clear you have root 2 plus root 3. But this thing, is the smallest field that has root 2 plus root 3. So, so okay. Okay, so is everyone good that this is, 4? So does everyone agree that if I show this is 4, then by tower law, this must be 1, right? Does everyone agree? Okay. But if it's 1, then then by definition, the two fields are equal, right? So this is just dimension 1, right? The answer would be dimension 1. And the basis is just 1, right? Because the two fields are equal. So method 1, let me just say method 1. There are many ways to do this question, but method 1 would seem like the easy route, right? Because your first intuition would be to ask what is this part, right? And that's pretty much method 1. We have to show it's degree 4. So you do your, the trick. Let's see, alpha minus root 2 is root 3. So what do I get? I get alpha squared minus 2 root 2 alpha plus 2 is 3. Negative 2 root 2 alpha is, what is that? 1 minus alpha squared? Yes. Okay. So now I get 8 alpha squared. If I square both sides, I get 1 minus 2 alpha squared plus alpha to the 4th. And from here, 0 is 1 minus 10 alpha squared plus alpha to the 4th. So we are a root of x to the 4th minus 10x squared plus 1. Everyone follow so far? This is the old-fashioned way. We do it explicitly. We try to find this explicitly. Okay, so so what do I want from what do I want to know from this if I want to show this is degree 4? Like what do I need to know about this polynomial? Yeah, yeah, irreducible, right? So I mean this really is just, you just argue. So you argue that it can't be split to 2, right? So so if it was if it had a root, right? If it was a root of this thing, um it can't factor as 3, 1, right? Because if it's 3, 1, then you're the one would just be, you know it would be, I mean, clearly q of root 2 plus root 3 is not q. So we assume that it's not a product of two quadratics. Oh, sorry, what am I doing? C and D. Okay, so this is actually pretty nice because from the fact that this is 1, I know either B is 1, D is 1, or B is -1, D is -1, right? Everyone agree? Again, you had a theorem that said if you're reducible over Q, you're reducible over Z. So we could assume these elements are integers. So from here, right? How do I say this? From here, we assume, let's assume this case, yeah? And then we do something similar. But we also know, I'm gonna erase this now since this is just finding the polynomial, right? From the x cubed term, the x cubed term is 0, right? Like there's no x cubed term here. So what's the x cubed term when I FOIL on the left hand side? It's it's just a plus c. Agree? Like the coefficient. Agree? Because it's x squared times cx and x squared times ax, right? So I know that this must be 0, so a is minus c. And so let's consider the b equals 1, d equals 1 case. So I have x squared plus ax plus 1, x squared minus ax plus 1. In which case, what's the x squared term? The x squared term is I multiply these two and I multiply x squared with 1 and x squared with 1, right? So I have 3 terms. I have the coefficient negative a squared plus 1 plus 1, right? And the x squared term should be -10. Yeah? So negative a squared is to -12. A squared is 12. A is what? A is square root of 12. And this is not in Z. And I mean, and it's not even in Q, right? So so that, I mean, like this is contradiction. And if b equals -1, d equals -1, then you have x squared plus ax minus 1, x squared plus ax minus 1. And then the square term is now, what is it? Oh, sorry, minus ax. So negative a squared, is it -1 minus 1 now? So negative a squared is -8. So a squared is 8, and a equals square root of 8. This is not in Z or Q. Yeah. If you're not comfortable with that lemma, it's not even in Q. So you're gonna get a contradiction. So from here, right? Like you can't factor as product of two quadratics. So this thing is irreducible. Yeah. And I mean, to show the degree 3 times degree 1, right? I mean, if it's degree 1, if you factor to degree 1, you would have a root, right? A root in Q, if you like. And then you can use rational root tests if you like. Yeah, you can plug in 1 and -1 and then show those are not roots. But in any case, this is irreducible. So this is degree 4. So this must be 1. Yeah, degree. And obviously my basis, this is degree, it's just 1, right? Does everyone understand method 1? We do it like brute force, sort of. Yeah. Okay. We could do it our way. So if you're expecting this is 4, so if I expect Q adjoin root 2 root 3, Q adjoin root 2 plus root 3 is 1, then that means these fields are equal, right? And it's pretty clear that we have one way, right? I mean, this thing is certainly bigger than this thing, right? It's contained, and this thing contains this one, right? But this is the field that the smallest field that's contains root 2 and root 3. So if I show this thing has if I show this field has root 2 and root 3, I am done. Yeah, because that means I have the other direction. So fields are equal. Everyone agree? Yes, no, confused. Okay, well, let's just brute force it. So if this is in my field, well, I could square it, right? I could, I have the multiplication operation, so I can multiply it with itself. So what am I going to get? I'm going to get 2 plus 2 root 6, right? Plus, I don't really care what this is, 3. So 5 plus 2 root 6, whatever this is, right? Now, 5 is in this field, right? I have 5, so I can subtract 5. I mean, I have all elements of Q, right? And 5 is in Q. So I can subtract 5. Now 2 root 6 is in this field. Now 2 is in Q. So I certainly have a half since I'm a field. So I can multiply by a half. I'll put arrows instead of equal. So now I know this field has root 6. Yeah? Does everyone follow so far? Am I going too fast? Okay, well, from here, I have the element root 2 plus root 3, right? So I could certainly multiply it with itself, and I still remain in my field. Agree? So I multiply by itself, I get this. I simplify, right? Now, this element is in my field, right? Plus root 3. 5 is certainly in here because, 5 is an element of Q. Agree? So their difference is also in there, right? A field is a group. It's closed under multiplication operation, right? It's closed under multiplying, adding inverses, right? So I do exactly that. And I get 2 root 6. Does everyone follow? Yes, no. Okay, and same idea, right? 2 root 6 is in my field. 1/2 is in my field. So if I can multiply it now. So I get root 6. Now I know I have this. So let's multiply by root 6. And what you're going to see is this is 2 root 3 plus 3 root 2. Yeah? So this is in my field. Now, this is brute force, by the way. Now I can multiply this by 2, right? And I get 2 root 2 plus 2 root 3, right? Now this is also in my field because each of these elements are. And now since both are, I can subtract. And now root 2 is in my field. And if root 2 is in my field, root 3 is in there, right? Because I have this. I have this. So now I can subtract and get that this is in here. Everyone see that? So this is like brute force way to show the fields are equal. You just show from root 2 plus root 3, you can get the elements root 2 and root 3. That's like method 2. Does that make sense? I mean, all this is you have to think, yeah, it's just brute force. It's not like a set way, right? You just do operations and try to isolate root 2 and root 3. So I would say method 1 would be more systematic. Yeah. But I'm just showing you, if you're not convinced that these two fields are equal, well, it turns out they are. Everyone good? So why can you stop at square root 6? So yes, but how do I know those are in my field? Like, yeah, like I agree. Like if I had if I had one of them, then I have the other because I could say square root of 3 is, well, this thing inverse. Yeah. But how do I know that this is in my field? I mean, okay, cool. Everyone else good? If so, I mean, hopefully that's enough examples so for you to start understanding algebraic extensions. So this is normally how arguments go, right? It's Tower law, prove irreducibility. It's just pretty much that. Like it's, I mean, for the formal for the theoretical proofs, it's just based off these, right? So once you have these examples set in stone, it's really just the theoretical part should come smoothly. Yeah. Okay. Yeah. So maybe next time we'll do some theoretical questions. So today I just wanted to do numbers. So okay. I will see.